Hello and welcome to the video. This video is going to be all about the second derivative of a function. So basically, we're going to go over what the second derivative can tell us and basically just some uses of it in calculus. So just to recap, to get the second derivative of a function, let's say you have some function f of x. To get the first derivative, you just take a derivative. So you get f prime of x, but you can differentiate again. If you differentiate once more, you get f double prime of x. This is the second derivative. So, pretty self-explanatory there. To get the second derivative, you just differentiate twice. Now, what is this really telling us? Remember, the first derivative tells us how a function is changing. So this tells us how f is changing. The second derivative, on the other hand, tells us how f prime is changing. So basically, the second derivative tells us how the function's rate of change is changing. So if the function's second derivative is greater than 0, that means that f prime of x, the first derivative, has to be increasing. That's similar to how when f prime is positive, f of x is increasing. On the other hand, when f prime of x is less than 0, f prime of x is decreasing. Like how f prime of x being negative means that f of x has to be decreasing. Now there is one case that we didn't cover. If f double prime of x is 0, what this basically means is that your rate of change is neither increasing or decreasing. So this often is an inflection point. It doesn't always mean an inflection point, but it always means that your rate of change is staying the same. It's not changing at that point. Now, let's just talk about concavity for a second. So you probably heard the term concavity in a pre-calculus course. Basically, if you recall, when the function is concave up, its rate of change is increasing. And that generally looks something like this. So notice your function can be decreasing, like from here to here, it's decreasing. But overall, its rate of change keeps increasing. That's the kind of shape you expect where a function is concave up. Now, where a function is concave down, it'll look something like this. Now, just because the function is concave down doesn't necessarily mean it's decreasing the whole time. If you notice, the function is decreasing here, but over here, the function is increasing. So all it means is their rate of change is decreasing. But if you recall, we just said that the second derivative tells us whether the function's rate of change is increasing or decreasing. So we can connect these ideas of concavity in the second derivative. What we're going to say is when a function is concave up, its rate of change is increasing, right? But when the function's second derivative is positive, its rate of change is also increasing. Therefore, when the second derivative is positive, the function must also be concave up. Oops, I wrote concave up here. I meant concave down. Now, a similar argument can be made for a function that's concave down. When the function is concave down, its rate of change is decreasing. But also, when the second derivative is negative, that means that the rate of change is decreasing. Meaning, we can connect these two ideas and say, when the second derivative is negative, the function is concave down. So, to recap, basically the second derivative tells us how the function's rate of change is changing. But that's very similar to the idea of concavity, so we can connect these ideas and say, when f double prime is positive, the function is concave up. When f double prime is negative, the function is concave down. Now let's look at what an inflection point is. Alright, so you might have heard the term inflection point in a pre-calculus course. Now, what this means, what an inflection point is it's a place where your function's rate of change switches from increasing to decreasing, or vice versa. So essentially, it's where your concavity switches. So this means that f prime switches, your first derivative switches from increasing to decreasing, or vice versa. Remember, your first derivative is just your rate of change. So this is saying the same thing as that definition you might have heard in pre-calculus. Well, f prime switching from increasing and decreasing, what that means is that f double prime, your second derivative, switches from positive to negative or vice versa. And think about where a function switches from positive to negative. That usually happens where a function crosses the x-axis. So like here, it switches from negative to positive, but not necessarily always. For example, take 1 over x. 1 over x switches from negative to positive, but it does not have a 0 where it switches. So basically what I'm trying to say is an inflection point will often happen where f double prime, the second derivative, is 0, because that's usually where it'll switch from positive to negative, or vice versa. But it doesn't necessarily have to be. So what you want to look for is places where f double prime is 0 or undefined, because those are the places where f double prime is going to be able to switch from positive to negative or vice versa, and thus those are the places where your function could have an inflection point. Now, if we look at this function that we have here as an example, y equals x to the 1/3, if you think about concavity, you can kind of think of it as looking like a bowl. So when a function is concave up, it's going to look like a bowl that's facing upwards, so like this. When a function is concave down, it's kind of going to look like a bowl that is facing downwards, or like a frown, so like this. So our function here, it looks like it switches from concave up to concave down at x equals 0. But how do we show that? Well, our function is given by x to the 1/3 plus 2. To get our first derivative, y prime, we just take a derivative. We get 1/3 x to the negative 2/3. And then that constant just goes to 0 when we differentiate it. Now, to get our second derivative, which is what we're going to test, we just differentiate y prime. So 1/3 out in front, and then using the power rule, we bring the power down and then decrease the exponent by 1. So 1/3 times negative 2/3 x to the negative 2/3 minus 1. That's negative 5/3. So this is negative 2 over 9 x to the negative 5/3. Because of this negative, we can bring this x to the negative 5/3 to the denominator and make the exponent positive. So we'll get negative 2 over 9 x to the 5/3. Okay, if you notice, when we plug in 0, this whole thing will be undefined because we have x to the 5/3 in the denominator. So this is a possible inflection point because y double prime, our second derivative, is undefined at x equals 0. So let's plug in a point on each side just to test if this is an inflection point. So if we plug in something that's negative to the left of 0, let's try negative 1. Negative 2 over 9, negative 1 to the 5/3. Well, negative 1 to the 5/3, that's negative 1 to the 5th, and then the cube root of that. Negative 1 to the 5th is just negative 1. The cube root of negative 1 is just negative 1, so negative 2 over negative 9, that's 2/9. That's positive. So the function must be concave up for x values that are negative. And now if we plug in an x value that's positive, let's try 1. We get negative 2 over 9, 1 to the 5/3. 1 to the 5/3, this is just 1, so we can ignore that. That's negative 2 over 9, and this is negative, meaning that our function must be concave down, like we said, or like we predicted, for x values that are positive. Meaning, because our function switches from concave up to concave down, this indeed is an inflection point. So I was just testing that and kind of showing you. But now let's do another example. Alright, for this problem, it first wants us to guess where the function is concave up and down. And then after that, we're going to test using the second derivative to see exactly where the function is concave up and down. And also we're going to see if we have any inflection points and where those are. So if I had to guess, remember a function is concave down when it has this downward bowl shape, so like a frown. And I see that right here. Now, if I had to say, I feel like the function kind of switches somewhere around here. So maybe it's concave down for x values from negative infinity to like -1 to negative 0.5. So somewhere around here it's going to switch. And then it has this upward bowl shape, like a smile, for x values over here that are greater than -1 to negative 0.5. So I would say it's concave up for x values from -1 to negative 0.5. When I say 2, I'm just kind of giving a range because I don't really know exactly where, just based on the picture, it's concave up or down. And I would say it just keeps on being concave up. Okay. Now that we've kind of given our guess, let's use the second derivative of this function to find where it's concave up and down. Well, our function is given by x cubed plus 2x squared plus 3. To get our first derivative, we differentiate once. We get 3x squared by the power rule plus 4x, because 2 times 2, and then reduce power by 1. And that plus 3 just goes away when we differentiate it. Our second derivative is given by 6x plus 4, because we bring this 2 down, but it gets multiplied with the 3. Now, we just need to solve for where this is positive and negative. So let's set this equal to 0 to find where the divide between positive and negative second derivative values will be. So 0 equals 6x plus 4. This means 6x is -4, which means x is -4 over 6, which is -2/3. So if the function is going to switch between concave down and concave up, it has to do it right here. Now let's plug in a value to test where this is positive and negative. So something less than -2/3, let's try -1. 6 times -1 plus 4, that's -2. So because we plugged in a value less than -2/3 into our second derivative and we got a negative value, this means that our function must be concave down for x values less than -2/3. So thus, we are concave down between negative infinity and -2/3. And we're not including -2/3 because the second derivative is 0 there. Now let's plug in something that is greater than -2/3. Let's just do 0 because it's easy. So 6 times 0 plus 4, that's just 4, which is positive. Meaning for x values that are greater than -2/3, our second derivative is going to be positive, meaning that our function will be concave up for x values between -2/3 and infinity. Now, if you notice, our second derivative switched from negative to positive at x equals -2/3. Because of this, we must have an inflection point at x equals -2/3. So, our guess that our inflection point was between -1 and -0.5 was actually correct, because -2/3 is between -1 and -0.5. So, our inflection point is about there. Alright, now let's go over the second derivative test. Alright, so I mentioned the second derivative test before in this video, but what is the second derivative test? So, the second derivative test is kind of similar to the first derivative test in that it can help you determine if a critical point is a maximum or a minimum, but it is a little bit more limited. So, let me just describe it and then I'll talk about what I mean. So, if the function f is defined in an open interval containing x equals c, so if it's defined around x equals c, and then f has to be twice differentiable at x equals c. So the first derivative and second derivative are defined at x equals c. And f prime of c is 0. Then if f double prime of c is greater than 0, so the second derivative of f of x at c is positive, then f must have a local minimum at x equals c. So what this is saying basically is if f is concave up at x equals c, then that has to be a minimum. So recall, a concave up shape kind of looks like this. So it makes sense that if this is a critical point where the slope is 0, you would have a minimum. Now, if the function is concave down at x equals c, then f must have a local maximum at x equals c. So concave down shape looks like this. So it makes sense that you'd have to have a maximum if your slope is 0 there. And if f double prime of c is 0, so the second derivative at x equals c is 0, then the second derivative test is inconclusive. So I talk about the fact that this is a little bit more limited than the first derivative test. First of all, it can be inconclusive, unlike the first derivative test. So if your second derivative is 0 at the critical point, then you can't really say anything based on the second derivative test. Also, notice our critical point needs to be a critical point where the slope is 0. So it needs to be somewhere where it kind of levels out. It can't be somewhere the slope is undefined, whereas with the first derivative test, we don't really need to test at the point itself. We just test points on each side. So that's why I mean it's a little more limited. You need to have a critical point with the slope being 0, and you also can be inconclusive. But it is kind of nice in the sense that you don't have to test 2 points, like one on each side. You only need to test 1 point, which is the critical point itself. So anyways, now let's do some practice with the second derivative test. Alright, so for this problem, we have y equals x cubed minus 12x plus 5, and we want to use the second derivative test to find out which critical points are minimums and maximums. Because x cubed minus 12x plus 5 is a polynomial, we know that all our critical points are going to occur where our first derivative, or our slope, is 0. Because the derivative of this polynomial is also going to be a polynomial, none of the places on that polynomial are going to have undefined outputs. Anyways, let's find the first derivative. Y prime, the first derivative, is d over dx of x cubed minus 12x plus 5. Using the power rule, we get 3x squared minus 12. Now, we need to set this equal to 0 to find all of our critical points. 3x squared minus 12 equals 0. If we add 12 to both sides, we get 3x squared is 12. If we divide both sides by 3, we get x squared equals 4, meaning that x has to be plus or minus 2. Now, we have our critical points at x equals 2 and x equals negative 2. Let's find our second derivative, y double prime. That's going to be, well, the derivative of our first derivative. So derivative of 3x squared minus 12. That's just 6x because we multiply this 3 and this 2, and we bring the power down by 1. And then this constant just goes away. So our second derivative is just 6x. So now we need to test our second derivative at each of our critical points. Let's try x is positive 2. Well, our second derivative when x is positive 2 is just 6 times 2, which is 12. So our second derivative is positive at our critical point of x equals positive 2, meaning that we're concave up, which means that we need to have a minimum at x equals 2. Now, if we test x equals negative 2, 6 times negative 2 is negative 12. So our second derivative is negative at x equals negative 2, meaning we're concave down, which means that we'll have a maximum. So we'll have a maximum, a local maximum, at x equals negative 2. Now, you could plug these x values of the critical points back into the original function to see the exact points where these critical points happen, but that's more of an algebra problem than a calculus problem. So I'm just going to leave it like this. Okay, so one more problem. For f of x equals sine of 2x minus x, for x values between 0 and pi, identify the x coordinates of the critical points and the inflection points, and then we need to determine if those critical points are maximums or minimums using the second derivative test. So first step is to find the critical points and the inflection points. So we're going to need to take a first derivative and a second derivative. Our first derivative, f prime of x, is going to be the derivative of sine of 2x minus x. So the derivative of sine of 2x, we're going to need our chain rule. Our outside function is sine, our inside function is 2x. So the derivative of the outside evaluated at the inside, that's cosine, and then of the inside is 2x. And then the derivative of the inside is just 2, so times 2. And then the derivative of minus x is just minus 1. Okay, now to find our critical points, we set this equal to 0. And remember, we're only looking for x values that are between 0 and pi, excluding pi. So if we set f prime of x equal to 0, notice all of our critical points are going to happen where our function has a first derivative of 0, because there's nowhere where we'll make the first derivative undefined. So we know that f prime of x is cosine of 2x times 2 minus 1. That's 2 cosine of 2x minus 1. And we set that equal to 0. So we add 1 to both sides, and then we would divide by 2. So we would get cosine of 2x is equal to 1/2. Now let's think of a unit circle. The x and y coordinates of this unit circle, respectively, tell us the cosine and sine of our angle centered at the origin. So where cosine is 1/2, that happens right here. And where this happens is at an angle of pi over 3. And if we think about kind of going the other direction, but taking away pi over 3, we get minus pi over 3. But we're kind of thinking about positive values, so we can add 2 pi to this, because that's a coterminal angle. So that would just be 6 pi over 3. So overall, our positive angle would be 5 pi over 3. So those are the two places in the unit circle where cosine would be 1/2. But you might notice 5 pi over 3 is greater than pi. The reason why that doesn't really matter for us right now is, well, we'll have two separate equations. We'll have 2x equals pi over 3. 2x is 5 pi over 3. When we divide both sides by 2, we'll get x is pi over 6, and x is 5 pi over 6. Because we have that 2, and then we had to divide by 2, both of these angles are going to stay within pi. So these are our critical points. Now, to find our inflection points, we need to find where our second derivative changes signs. So let's find our second derivative. F double prime of x is just the derivative of f prime of x, which is 2 cosine of 2x minus 1. This minus 1 will just go away when we differentiate it. Now, we can just pull this constant out. The derivative of cosine is minus sine, and the chain rule says we need to evaluate that at the inside. So minus sine of 2x times the derivative of the inside, which is 2. So minus 4 sine of 2x is our second derivative. Now we need to set our second derivative equal to 0 to find where it switches signs. Minus 4 sine of 2x equals 0. Well, we can divide both sides by -4. We get sine of 2x is 0. Where is sine equals 0? So we would get that our argument of sine, which is 2x, is equal to any multiple of pi, because that's where sine is going to be equal to 0. Every time you go from 0 and then pi around the circle repeatedly, you will have sine equal to 0. And here, k can be any integer. Alright, so this is what we found so far. We found that our critical points happen at x equals pi over 6 and x equals 5 pi over 6. And we found that our inflection points happen at x equals 0 and pi over 2. Now, the final thing to do is to find out if our critical points are maximums or minimums using the second derivative test. So let's do that. So for our first critical point, which happens at x equals pi over 6, if we plug that into our second derivative, we get minus 4 sine of 2 times pi over 6. And that's negative 4 sine of pi over 3. Well, if you think about a unit circle, what is sine of pi over 3? An angle of pi over 3 is like this. It's higher than pi over 6. And so it's going to happen where your x-coordinate is smaller than your y-coordinate. And that's going to happen where your y-coordinate on the unit circle is square root 3 over 2. So you're going to minus 4 sine of pi over 3 is just going to be your y-coordinate. So that'd be square root 3 over 2. and that 4 and 2 will simplify to negative 2 square root 3. So the second derivative is negative at x equals pi over 6. So that means that pi over 6 is a maximum. Now let's check 5 pi over 6. So the second derivative evaluated at 5 pi over 6 is just minus 4 sine, and then 5 pi over 6 times 2, that's just 5 pi over 3. So negative 4 times, what's sine of 5 pi over 3? Well, that's the same thing if we subtract 2 pi, because that's going to be a coterminal angle, meaning it will have the same sign. You get just negative pi over 3. So kind of the reverse of pi over 3. Well, it's going to have the same y-coordinates of pi over 3, but just reversed. So it's going to have a sine of negative square root 3 over 2. And these negatives will cancel out, and we'll just get 2 square root 3. Meaning that because our second derivative is positive at x equals 5 pi over 6, we have to have a minimum at 5 pi over 6. Okay. So this is our conclusion. Our critical points are at pi over 6 and 5 pi over 6. Our inflection points are x equals 0 and pi over 2. And pi over 6 is the max and 5 pi over 6 is the minimum. Now, one thing I forgot to kind of verify is that our inflection points are actually inflection points. I just found the places where the second derivative was 0. I didn't really test to see if it changed signs. Now, because our second derivative is minus 4 sine of 2x, it's always going to switch at its zeros. So we didn't technically have to check that, but it's good practice too, so I'm just going to do that real quick. Alright, so this is me checking at x equals 0, that it switches signs. As you can see, if I test an x value that's less than 0, so like negative pi over 4, I get that the second derivative is positive. If I test an x value that's greater than 0 for the second derivative, I get the second derivative is negative, meaning that it switches signs at x equals 0. So that means that this does have to be an inflection point. Okay, and when I tested x equals pi over 2, this is what I get at an x value less than pi over 2. So like pi over 4, I get negative 4. At an x value that's a little bit more than pi over 2, I get 4. So it switches from negative to positive, meaning that because the second derivative switches signs at x equals pi over 2 has to be an inflection point. Alright, so that is all of the practice. Alright, thank you for watching. I hope that you found the video helpful. In the next video, I'm pretty sure I'm going to be going over curve sketching, so check that out. Anyways, I hope that you have a good rest of your day, and bye-bye.